In this section, what we're going to be doing is taking a look at going back through some of the techniques of integration and the theories of integration, since Calculus 2 is really heavily predicated upon one's ability to perform integrals. And you may remember at the end of Calculus 1, you started doing a little bit of integration, and maybe the last topic you did was a U substitution or finding areas of something of that nature. And that's what we're going to basically go back over, is we're going to look at how we can relate areas, integrals, as well as these animals called Riemann sums together, right? So in this section, we want to make sure that we understand the relationship between those three entities. We're going to be able to approximate areas or integrals using a left-hand rule and a right-hand rule and a midpoint rule. We're going to apply some properties and some rules of integrals, and then we're going to be able to evaluate integrals using geometry. So keep those in mind as you're going through, that those are the big overarching topics. Two main problems in calculus, one of which is the slope problem, explored mostly in Calculus 1 with the derivative. The second major problem in calculus is the area problem. And one of the most fundamental problems in mathematics is being able to compute the area bound by a curve. And of course, we can do that, as we did in Calculus 1, by breaking up into rectangles. Okay, so you can see over here where I'm kind of drawing this. We're just breaking up that area into rectangles. And you might ask, well, why do we use rectangles? Why don't we use dodecahedrons or something of that nature? It's because a rectangle is really easy to compute. You might remember that the formula for being able to compute an area of a rectangle is base times height. And so it makes it really easy for us because the height is actually going to be represented by the function value at that specific point, and the base is going to be partitioned into delta x, all right? And essentially what we're going to do is we're going to break it up into a number of rectangles, and delta x is going to be equal to b minus a over n. Now, the interval is a to b, all right? So this is a and this is b in our interval, and n is going to be the number of partitions or the number of rectangles. In this case, n is equal to 4 because there are 4 rectangles, and the same thing on this one. Right? Ultimately, we theoretically like to have an infinite number of rectangles. If you think about that, an infinite number of rectangles would allow less error. Okay, and the more rectangles you have, the less error that you're going to have in your drawing. And eventually what we're going to do is we're going to eventually theoretically go towards infinity with the number of rectangles under the curve. We're going to add all those areas up. So remember, f of x is going to be the height and delta x is going to be the base. So this is really base times height, or in this case, height times base. So really, a Riemann sum just adds up all the heights times the bases, all the rectangles, and theoretically, again, we're trying to go towards infinity. And the way we represent that nicely in mathematics is by an integral, right? So that's essentially an overview of the large problem that we're faced with with the area. Now, before we can start evaluating these definite integrals using some basic fundamental rules, we're going to go back and we're going to revisit the idea of a definite integral in the general context. And then we're also going to take a look at being able to evaluate by using some approximations and some geometry before we can start using something called the fundamental theorem of calculus, which you might remember from Calculus 1. All right, so before we get to any of that, there are some properties of integrals that you should be cognizant of, and you should have these memorized at some point. Some of these are really basic, and some of them are really intuitive, and some of them require a little bit more, I guess, fleshing out. But the first one is that if you reverse the bounds on an integral, okay, so if you take a and b and you swap them, what's going to happen is you're just going to have the opposite of the value of the integral, right? So if you know what the value is and you flip the bounds around, just take the opposite. If you have the same upper bound and the same lower bound of a function when you're taking the integral, that area is 0. And theoretically, that makes sense. Let's say we have a curve, and this is A, and we're going from A to A. Well, there's no area. It's just a straight line. All right, so that's what we're worried about with respect to that one. If we have a constant function, like a 5 or a pi or an e or something like that, ranging from A to B, we're just going to take that constant and multiply it by b times a. Although this one we're going to see a little bit later in the next section of videos, where we could just evaluate that by just using a fundamental theorem of calculus, although certainly this one's valid. If you have a constant times a function, you can factor the constant on the outside of the integral and then just evaluate the integral. All right, so C is any sort of numerical constant or variable constant when you get to Calc 3 or multivariable calculus. If you integrate the sum or the difference of two functions, then what that means is that you could just integrate each function individually, all right, or find the areas of those, okay? So sums and differences, basically, you can distribute the dx and the integral sign, and you can evaluate that into two integrals, all right? We'll see that a little bit later. And then finally, if you have some number in between a and b, let's call that c, right? Then you could split up an integral such that if you have a to b and then b to c, and it's continuous, then you could just take the integral from a to c. And think of it this way, you can go in reverse of that as well. So you can go backwards and split it up if there's some number in between a and c called b. All right, so again, have these memorized, okay? These are some really fundamental sorts of calculus properties, all right? So let's go ahead and do some example problems of this, and none of these are too difficult. So let's say we have the integral from 0 to 5 of a function is equal to 3, and the integral from 0 to 7 of a function is negative 10. If I want to find two integrals, or double the integral of f of x dx, remember, we can rewrite this by using that constant rule, right? So if we go back up just a little bit, we could factor a constant to the outside. So this could be two integrals from 0 to 7 of f of x dx. And we know that the value of that is already negative 10. So that just becomes 2 times negative 10, which is negative 20. All right, so really easy to evaluate that. Similarly, if we went from 5 to 7, okay, so we have from 0 to 5 and 0 to 7. So a way to think about this might be that the function looks something like this. So from 0 to 5, you have positive 3, right? So let's call this 3, all right, for some reason. And then from 0 to 7, the whole total, so let's call this 7 right here, and let's call this 5 right here. And I know that's not number line accurate or anything like that, but the whole thing is negative 10. Right? So we can kind of split that up, and we can say, well, this is equal to the integral from 0 to 7 of f of x dx. All right. And then we want to try to subtract out something. So we could say minus the integral from 0 to 5, because that would just leave us with 5 to 7 of f of x dx. So in this case, that's going to wind up being, we know that already that's negative 10 minus 3, and that's going to be negative 13 for us. Okay, so we're just using this rule of being able to divide up an integral right here. Okay, if we can find some intermediary value, then that's how we're going to try to split that up. This one's pretty easy. We have the integral from 5 to 0 of f of x. Well, we have the integral from 0 to 5, so that's just the opposite of the integral from 0 to 5 of f of x dx. So we're just flipping that over, and that's going to be equal to negative 3. And then finally, we have the integral from 7 to 0 of 6 functions dx. All right, so we're going to use this rule where we're going to factor the 6 out, but we're also going to use the rule where we're going to flip the bounds and make the integral negative. Okay, so when we finish this off, that's going to be the opposite of 6 integrals from 0 to 7 f of x dx. All right. Now we already know what the value of this is. All right, that's negative 10. All right, that's given to us right here in the original problem. And so we're going to wind up with negative 6 times negative 10, otherwise known as 60. Okay. All right. One last example before we finish this off, and then we'll stop this video and we'll start another one. Let's say we have the integral from 0 to 1 of x squared plus 2 dx is 7/3. We're going to find the value of each of the following. All right, so um, notice right here we have the same bounds, so that's good. And we have 3x squared plus 6. And we could rewrite this by factoring a 3 out. And we could write this as x squared plus 2 dx. Well, we know what the value of this is. That's just 7/3. So we get 3 times 7/3 or 7. Nice and easy. Similarly, we have from 0 to 1, but we have a factor of 10. All right, so the bounds are flipped. So let's make this a negative and factor out a 10, and we're going to flip the bounds around. 0 to 1, x squared plus 2 dx. And we know what the value of this is. This is a value of 7/3. So we get negative 10 times 7/3, or negative 70/3 is going to be the value of our integral. All right. So we're going to do a few more examples in the next video, but this is just an essential overview of some of those rules of being able to work with our integrals.